Welcome to the last technical session of EFCS 2023. In this session, we have two speakers. First one is Dr. Nygil Thomas, and secondly, Dr. Nitin Raj. Let me introduce the first speaker of the session, Dr. Nygil Thomas. He is an assistant professor at the Department of Chemistry, Nirmalagiri College, Kannur. He completed his PhD on layered materials from St. Joseph's College, Bangalore, under the guidance of Dr. Mikhail Rajamati, and did his postdoctoral fellowship at Fritz Haber Institute of Max Planck at Germany from 2012 to 2013. In 2013, he joined as an assistant professor at Nirmalagiri College, and he has published more than 50 international publications and 5 book chapters in his credits. He is a reviewer of around 30 journals. He has received many prestigious awards and fellowships, including ICAN Young Scientist Award and Human Insulin Project Award from Biocon. He is a principal investigator of many major and minor projects from UGC, DBT, and KCST. His research interest includes heterogeneous catalysis, oxygen evolution reaction, supercapacitors, electrochemical sensors, and nanomaterials. With this brief introduction, I would like to call Dr. Nygil Thomas for his wonderful presentation. Please, sir.
Thank you, Yusuf sir, for kind introduction. First of all, I thank Farook College and the organizing committee of this conference to inviting me here for this talk and also giving me the Young Scientist Award. Last many years, you have this program running here, but unfortunately, I couldn't be a part of this program. So this is the first time I'm coming to Farook College, and my association with the Farook College started long back. I still remember the BSc students of Farook College coming all the way to my college to take the powder X-ray diffraction pattern. So I value your enthusiasm and spirit. I am very much impressed. I keep telling my students. So I give a big thanks and also a big hands off to good students here. So let me start. Let me start with a little bit old work of mine to what I am currently doing. Okay? So imagine that if we couldn't produce a chemical commercially, then half of the world population would not exist. Can you name which was that chemical or which is that chemical? Anybody? Any student? Okay. Okay, fine. That is ammonia. Okay? And this ammonia story is very interesting. And why I tell this little bit of this story is because my institute earlier was named after Fritz Haber. It's called the Fritz Haber Institute of the Max Planck Society, where we did a lot of work on the heterogeneous catalysis. So today I thought, to this audience, I will try to introduce a little bit about the catalysis, and I will show you some of the simple things. Okay, so this is the process where you have, when you had a severe need of ammonia, you must be knowing this importance of this chemical because you want it for thousands of reasons. And if you read the story of this ammonia synthesis, definitely you will have a lot of interest to study equilibrium and lots of chemical concepts. So I keep telling my students, you relate your studies to the real life problems and also some history, then it will be interesting. Otherwise, if you just write H2 plus N2 giving ammonia, looks simple, some very silly reaction like that. But it's very, very difficult one, you know. Okay. Okay, and I was just going through before this talk the Nobel lecture of Carl Bosch, who actually commercialized the ammonia synthesis. So he was telling, he started his talk by giving 3 challenges for the commercial production. One was the supply of raw materials. That is nothing but the hydrogen and nitrogen. And then the next one is manufacture of effective and stable catalyst. Okay, and the third one was the design of the reactor. Okay, he dealt all these problems simultaneously and solved it. So, but now with the ammonia synthesis, we have new challenges. All 3 earlier challenges were already addressed, and we have huge amount of ammonia produced with which we could do the green revolution, all those such things. But now you see that the whole energy, world's total energy supply, 2% is used for only this reaction. Okay, and also you see the emission of carbon dioxide per kg of ammonia. Okay, and the process is 100% fossil dependent, right? So I will in a later slide, I will show you how these challenges also can be addressed. Okay, now let's move on. In 2005, this Nobel laureate, he wrote a book, and it says about the methanol economy. Methanol economy, that is, the process of synthesizing methanol, okay, from carbon dioxide and hydrogen. So that he proposed as a solution to the alternative to the fossil fuels. And why I talk about methanol a little bit today, because my project was on the methanol synthesis from industrial synthesis of methanol from carbon monoxide, carbon dioxide, and hydrogen, which is called the syngas. Okay? And methanol is, as you know, it's a liquid at room temperature, and you can convert methanol to so many products. And it is called a base chemical. Do you know what you mean by base chemical? Can anybody answer which is the chemical produced globally the highest quantity? Anybody from the audience? Okay, that's sulfuric acid. Like that, in 10 list, the top 10 list, methanol also is there, right? Okay. So these are the reactions associated with the methanol synthesis. You have carbon dioxide going to methanol and carbon monoxide getting hydrogenated to methanol, and all these reactions. It's a bit complicated, and my earlier institute was working more than 20 years on this problem. And also, I would like to tell that the catalyst for this industrial catalyst for this reaction has not changed last 50 years. Okay, we are using the same catalyst. But then a lot of research work has been done. Okay, so let me introduce a little bit about catalysis. Okay, as many of the other speakers told that it is giving an alternative pathway with a little bit less activation energy so that you have an easy path to this one. And I thought, actually, if you are ready, shall we synthesize a catalyst? Are you ready? Okay, good. So now we are going to synthesize a multi-million-dollar worth catalyst. Okay, that is called copper zinc oxide alumina. So we need to take some precursor materials. Simply in your lab, it's just a lab experiment. Copper nitrate, zinc nitrate, and some form of aluminum nitrate. That's all. You mix in certain ratio. Don't worry about the ratios much. You mix in some ratio. Can you see this reactor? Okay, and I'll talk a minute. And then you get a precipitate because you need to add some base to the solution, and then you get some precipitate, you wash it, dry it, you heat it, you calcine it, then you reduce it, then finally you have this catalyst. The first thing is like the precipitation, right? So this is a precipitator. This is actually, it looks a bit complicated because you have 2 dosing units, and simultaneously base and the metal nitration will be simultaneously dosed. Okay, to this one, so that we can keep the particular pH constant. This is called constant pH precipitation. And one interesting thing is that after coming from Max Planck, I thought I would buy this small reactor, this mixing unit. Then I asked a quotation from the Mettler Toledo. They sent me a quotation, and I was looking at the figures. I got really surprised. It was quoting 1.40 crores CR. Then I just called them and told, I think you are one zero or something, you put extra or not. Then they told that is the real price of this one. So that is the challenges we are facing. Okay, so now what you have to do, you have to manually use 2 burettes and try to do this one, okay? So that is just a challenge. And then, see, after the precipitation, the next step is sometimes it's called aging. So for the chemistry students, once we precipitated this sample and we went for a coffee, and while coming back, suddenly the color was changed. You see the color change between this. This is called aging. That means the catalyst, the precipitate is in the mother liquor, and then it's getting aged. But you see the quick changes here. So I keep telling my students, the chemistry is all about observation, and in your lab experiments, you need to observe very carefully what is the color change, why it's coming, why the precipitate coming, and so on and so forth. Okay, then we did a lot of work. Actually, the initial precipitate was the amorphous one, and then it is changed to crystallize automatically, and then we did a lot of analysis. And this is the strategy we follow, okay? And all these initial steps, catalyst remembers. It's something called a memory effect. The catalyst, the final catalyst, will recall where it has come from. Okay, which precursor it has come from, right? So this is one thing. This is called a temperature programmed reduction. This is called TPR. In this TPR, what we do, you take a catalyst in a long tube and you subject it to hydrogen in a very low concentration. Then your catalyst will reduce. Why you want to reduce? Because your actual catalyst is copper, zinc oxide, alumina. So when you reduce, when you supply hydrogen gas in a low concentration, and when you heat it, only copper oxide will become copper. And some slight things will happen to zinc oxide and alumina. It mostly will stay as zinc oxide and alumina only. Okay, the active phase is copper, but the copper alone will not work. When I was in the initial days, I was very curious. If copper is the active phase, why don't we take only copper precursor and start? Then I did some highly active copper precursor alone and started the reaction. Just in 10 minutes time, after getting the first run, the catalyst, all activity lost. Okay, so, sorry for this one. Okay, so you see the calcination temperature. This is the calcination temperature as you vary your TPR temperature. That means your catalyst is reducing, for example, here somewhere below 250 degrees centigrade, but in some case it is reducing 350 also. So that there are 100-degree differences is coming in the reduction temperature. For an industry, these numbers are very, very important. Even 0.5 degree temperature we can bring down for industrial catalysis, it saves a lot of money. Okay. Once you prepare the catalyst, and we look for, as you have already seen in the morning, you look for images, and particularly one work was like finding the active centers, and you have heard that if there are a lot of defects and boundaries and so on and so forth, your activity will be higher. And in this paper, this is our work, but unfortunately I couldn't be in this paper at that point of time. I did some work, but I didn't know the importance of a science paper at that point of time much. Now it has 2,500 citations, and it is considered to be the kind of a role model paper for the active site of copper, zinc oxide, alumina. Okay. I did work only after it come for the revision pub. Okay. Then these images you have seen is very nice images. You see this is like a 1 nanometer, and you see so many planes and tuning planes and other things. So I'll quickly go. You see this one, this is copper. This is a copper particle. You see how it's nicely covered and protected. So if you expose as such the copper nanoparticle, all the particles will agglomerate, and in 1 minute you will lose the activity. But if you can keep it in this way, you know these catalysts are quite stable. You don't believe it will be stable for more than 2 years in the industry reactor. Okay, so this is the plan we generally do. We have some kind of mesostructuring, then take the nanostructuring, and then activation and these ones. Okay, so when you ask which is the best catalyst, we try to do all these things. We need high surface area, and then we need defects, and we need the best catalyst will be in the mix. I have difficulty in controlling that. Sorry for that. Okay. So this is the original catalyst, how it looked like. This is a maybe very, very costly catalyst. And when I visited the Suit Chem, it's a company where all your MSc students, after that, you can also join. It's a German company where you manufacture catalysts. When I visited the R&D center in Kochi, they do almost like same thing. They just mix something, precipitate, and they sell the catalyst for millions of rupees, like this packet. Okay, and this is the biggest reactor in the Middle East. There are a lot of reactors, and we had to set up one reactor as such because we don't have the industrial reactor. So we had to build. My senior built the high pressure, high temperature reactor, and then this is the control, and this is how this is built. And also, you know, when I came back, I also wanted very much to do this kind of work, but you know, this needs so much of safety and also so costly, and how you can do it. We have to switch to new things. So, I mean, that is something we face, and this is me operating in the reactor side quite often. And okay, so let's stop the catalysis part there. And also, okay, one important experiment, we did it. So, students, do you see this reaction? Everyone? Do you see any curiosity in this reaction? Anything you feel? Anything, do you think? Anybody? Okay, because of time, I will go quite fast. Okay, the curiosity what we had is that these catalysts will work only in the presence of carbon monoxide, carbon dioxide, and hydrogen. It is not active if you have one component is not there, right? So the scientific community had a curiosity, which carbon, you know that methanol has only one carbon. So which carbon is going to methanol? Whether it's the carbon from the carbon monoxide or carbon from the carbon dioxide. That was a very valid question. It was answered in 1987. Only with a particular catalyst it was answered, but we wanted to see is it a generalized reaction or is it applicable to a wide range of this reaction. So of course, these kind of reactions are only possible when you have lots of funding, because it's a labeled gas is very costly. So what do? You label one component. Okay, instead of C12 CO2, you take C13 CO2 bottle, you buy it and try to do with the mass spec. Okay, I have not time to explain more. And this was really we call the whole department, we call the moment of truth. And the truth was that the final conclusion, let me tell, for any catalyst, whether it's a zinc containing or zinc free catalyst, for all the catalysts, the 95% or above of methanol is formed from carbon dioxide. Okay? But the interesting part is that without the presence of carbon monoxide, the catalyst won't work. Okay. And also I did a very long-term study. We did it. Okay, these kind of things you see, this is a catalyst, copper magnesium oxide. This is a very good catalyst, but it will only work from CO and hydrogen. If you have carbon monoxide and hydrogen, this catalyst will work very well. You have very good activity, and this paper is quite pending for last couple of years, and we are trying to finalize. Okay, and as soon as you have a ppm amount of carbon dioxide there, the activity is lost. You see, activity is lost completely. You see the red spots. And then what I did, I switched back to the carbon dioxide. I supplied little bit of carbon dioxide, the activity is gone down, then I switched back to the normal case, that's the mixture of carbon monoxide and carbon dioxide. Then over 7 days, it took 7 days, but you see this activity started picking up and then almost reaching the same point where we are starting. It's a long-term experiment. So we had a lot of open-end questions, what's the carbonate formation in situ and all those things. And while coffee session also we were discussing about some doing TEM to get these things, okay? But that is quite difficult in this case because, you know, we need to do the TEM of the reduced catalyst. When the reduced catalyst is exposed to the outside, immediately it will catch fire. Because, okay, so we need to immediately, after the reaction, we have to block the reactor, take the catalyst, convert it into a glove, into a chamber, and take that big chamber to the glove box, and then insert the temp grid to this one, and do this quite a lot of work. And there should not be any exposed to air. Like that only we did all these things, and this is again a cover page which we have written. This is a paper, the CO2 hydrogenation. Okay, and I told you that we need to address the new challenges with the ammonia synthesis or new challenges with the methanol synthesis. What are the new challenges? Because all these things are fossil dependent. Carbon monoxide, carbon dioxide, all these are coming from hydrogen, also especially coming from a fossil fuel background. Suppose if you wanted to produce, we have to leave the carbon footprint. We want, let's say, green hydrogen. Then we have to switch a little bit into other technologies. But the real motivation why I switched to electrocatalysis is because I have no fund or things to do the industrial catalysis. That's why I switched, although we say that this is the reason. Okay. So if you look at the hydrogens, everybody wants this one as a fuel, green hydrogen, because hydrogen you can burn it and then clean, you can drive your car and everything with a zero, this thing. Okay, so connected with this hydrogen, you have a lot of technologies and about oxygen also. These are the important reactions we nowadays trying to do, not all of them, but some of the reactions we are working on maybe last 2 years also. And these are the technologies where we need those reactions applicable. We have this fuel cells, water electrolyzers, metal air batteries. But mostly we study that small reaction as the individual reactions. We are not combining it, okay? Right, so these are, so in our group you try to address this very quickly. I can tell that all the industrially relevant catalysts are made of noble metals like ruthenium, iridium and platinum. Like many other groups, we are also looking for what about cobalt, nickel, iron, manganese, and let's say first row transition elements. And you know, all these things are we can manipulate with the transition metals. You know most of the things. And these of materials we have a lot of interest in spinels, perovskites, and also layered materials. We play a lot with these ones. And since I have only 6 minutes left, so let's little bit quickly go about these reactions. And I just wanted to show you one more thing what I was doing. Okay, let's look at this. If everybody can look at this, you have seen, you all synthesize one catalyst, but we were trying to see whether we can have a different method to synthesize materials. Okay. So last 5 years also, we did a lot of work on this very simple process. This is called a solution combustion synthesis. Okay, so let's see whether this will work. Can you all have a look at this left side? All right. Okay, sorry. Okay, you saw a combustion reaction. It's a very simple reaction. You need to mix a fuel and an oxidizer. Oxidizer is generally your nitrate. All your nitrate salts are oxidizers. And you have a fuel. We have almost like 20 plus fuels like urea, glycine, and so on and so forth. But the variety you can bring it there is that if you change the fuel, you can have a lot of variation in the materials. If you change the fuel to oxidizer ratio, you can tune many things. So these kind of nice porous materials you can make, and the synthesis time is just 2 minutes. 2 minutes you can get a complicated material. Okay, suppose, this is one very simple example. If you start with the nickel nitrate, you can have pure nickel oxide to even to nickel. Okay, you can have nickel oxide, nickel mixture, pure nickel oxide in different size, different morphology. All these can be tuned. Okay, so we did some substitution in the cubic nickel oxide. We did some substitution, and then we made almost like 50% substitution we could make. But I can clearly say that no other method so far reported substitution in the cubic nickel oxide actually. Okay, so you can tune the porosity. You can, starting from no pores to you can have an optimal pore size and things like that. That has to do a little bit with catalysis and other things. So we played a lot with the perovskite structures and also spinels and these things. And since not much time, I cannot discuss everything. And then some of the composite materials like MXenes and other things, and to improve our potential and bring it down to the relevant conditions. Okay, so I'm going quickly. And this is one project we are doing with the German group, but started from these things. See, what you see here, these kind of perovskites, LSCO, O3 and all, we can very finely dope this iron. You see the 0.2, 0.4, 0.6, 0.8, very clearly, like a series of samples with a very precise samples. But some of these series, our collaborators tried a long time with the precipitation techniques. It was not possible. So they were very interested to get this series, and these kind of industrial catalysis we are doing with new reactions like propanol oxidation and so on and so forth. And we also do lot of things. And Madam morning talked about the electrochemical sensors and some molecules. We extensively worked on some sensors. This is like, you see, kind of separation of biomolecules, like an HPLC kind of separation. We can have base-to-base separation with this electrochemical techniques, and we did a lot on dopamine, serotonin, epinephrine, those molecules. And we are also now, this is a medical manufacturing company called BTL. It's based in Czech Republic, and they are also a little bit interested to make some devices out of this. We use like carbon-based electrode, glassy carbon electrode, and so on and so forth. Let me quickly go. We also work on battery and supercapacitor. Not much about battery, but supercapacitor, different thing. And my last 1 minute, let me spend 1 minute on this slide where I worked after my MSc. This is a company called Biocon, and my project was to develop human insulin. I would say that this is the biggest project I have ever seen. What kind of problems? It's like just to the students. See, you have to address the diabetic problem of India, where out of 5, you have 3 diabetics kind of thing. Okay, to supply diabetic patients, you need to supply this insulin you need. So you need to manufacture insulin in tons. Okay, and this is the only Indian company developed recombinant DNA technology, and I was in this. And finally, this is like an Indian company with, you know that because the audience you see, most of them are young girls, and see, this should be really motivation. When I joined this company, Kiran Majumdar Shah was the richest lady in India when I joined the company. Now she's not. Okay, and also she was in the Prime Minister's Advisory Board and all. Many projects failed, but then this insulin was a huge success. Now, when I was there, the 1 kg was costing 30 lakhs. Initially, my seniors worked on the problem. We got 0.5 gram of insulin in one batch. For solving that problem, we need a lot of biotechnologists, microbiologists, biochemist, then chemist, and so many people. Around 500 scientists are working for one single problem. Finally, they solved it, and they have now I visited their Malaysian enterprises also. They have huge manufacturing facilities. From 0.5 gram to, we optimize the process where we can get the same amount of raw materials. We got 5.5 kg of insulin, 5.5 kg from 0.5 gram. That is what a chemist and a scientist can do. And finally, with this, I acknowledge my research group, and also, this is my wife, and they are all working very hard, okay? And thanks for giving me an opportunity to present our work. Thank you.
Yeah, so this is rather a little bit of a doubt.
Yes.
So you take a picture of that,
Yeah.
and from the top, right?
Yes.
And still some color is remaining.
Yes.
So this means that the combustion is incomplete?
Yes.
Okay.
Combustion is incomplete, but the product is pure.
I understand. I understand. So what is the reason for this incomplete combustion?
No, we can make it. For this photo, we can do the same reaction inside a muffled furnace, so the heat can come from all sides equally. Then it will go on completely.
Okay. Very nice. Thank you.
There are like a lot of figures of merits we look for a catalyst, like overpotential, current density, stability, etc. So which of these will you give more importance? Like what is the rate determining factor for the use of a catalyst in an industrial scale?
Yeah, your question is correct. Usually, I am not very much worried about the absolute value, because people say so much about, over potential. Right now, all the important papers are coming with over potential less than 200 millivolt. So if I send a paper with the 340, then you say, reviewers will, hey, what man, you are sending 350 like that. But I don't believe in it. We are trying to say science. We are setting a series of catalysts, and we are saying one parameter is varied, how that is affecting the catalytic property, not that absolute value. Why? Because this absolute value has not much value in a real process industry. There are other parameters like stability makes a very, very important contribution. You see, more than 20,000 papers are on this catalyst. Even now, Max Planck writes Science and Nature in this subject, but the catalyst has not changed, because industry is so reluctant to change the catalyst. We made, our project was from the industry only. We have given them much active catalyst than the currently running catalyst. But they are saying that to implement that for a 2-year reactor is a huge process. So they will try to push maximum with the old thing. Otherwise, there should be that kind of a significant improvement. This is glycine.
Glycine.
it's
And
a
have
very
you
simple.
ever tried any other fuels?
Yeah. We have a library of fuels, around 20 fuels, like urea and all. We have to worry about their decomposition temperature and clean burning. We utilize one important parameter. When I used a fuel, I see that some carbon is getting deposited. For certain cases, we need that carbon deposit on. For example, OER, that was the ACS on paper, we developed a method called carbon-assisted combustion. At the end of the thing, we get a fine coating of carbon, very small amount. You can't even detect with many types. But for the activity, that carbon makes a contribution for the activity.
And what was the main difference you have seen when you change the fuel of this combustion?
Yeah, you see, certain fuels needs 300 degree for the decomposition. So you will land up in a product which is very crystalline product. Okay? You see, maybe I am wrong, but nickel oxide, for example, I can synthesize like a 4 nanometer, 5 nanometer nickel oxide using this method, but I have not seen any literature so far with black nickel oxide. Usually because everybody has to heat it for 300 degree. Then it will go out of the nano regime.
Thank you. Thank you for that wonderful introduction. So whatever you have heard till now is from scientists. So I was also a researcher till a few years back. Then when you run into a hardcore industry like this, and in your native, you will consider yourselves to be lucky. So I'm a lucky person. I landed in a world-class company in my native. Actually, I stay here itself, just in front of the gate. Some of you might have seen me. My wife works here. So I'm a kind of a regular person here. So talking about my presentation, advanced technology of secondary refining and 3D printing in critical cast component. So first of all, I should define what I mean by a critical cast component. Yeah. So this is what we make. So this person is almost of my height. And literally there are many castings through which I can walk. And we make castings for petroleum, nuclear power, and yeah, many companies will be familiar to you. Siemens, KSB, Flowserve, Sulzer, like so many are there. So all are those. In case of a critical casting component, there are two things they demand. One is precision of dimensions and surface finish. Second is the material quality. And in the precision of dimensions, we have an entire department working there, and I belong to the person who is working on the materials, or I'm a metallurgist, to be precise. So till now, what you have heard is from people who are working in nano levels, micro levels, and in polymers, chemicals, etc. I'm basically a mechanical metallurgist. I term things in tons. So we basically manufacture castings up to 15,000 kg or 15 tons. So these are some of the components we make. So before I introduce what technologies we use now, or what are the advancements we adapted from the researchers like who presented before me here. So before those adaptations, I should say how we used to work. How is the conventional way of working on a casting? So conventionally, this is the oldest industry, one of the oldest manufacturing industries in the entire world, the casting. So what we make is, if we want a component of some shape, first we make a cavity of that shape, okay, which is basically called as a mold. And you melt a metal and pour into it. In hearing, the process is very simple. So this is a kind of manufacturing process which is called as subtractive manufacturing. You all will be familiar with the term additive manufacturing, right? So this is a kind of, we are doing subtraction. We are giving all the allowances, a path for metal to flow in, and the shrinkage allowances, allowances for machining, and allowances for grinding, welding, etc., and giving a riser to compensate the metal when it shrinks. That acts as, basically for engineers we talk, it's like a flywheel. Flywheel is what? It supplies energy when it is less. So it is like a reservoir. Yeah, basically we can say a reservoir. When this metal shrinks, it supplies. So like that, several additional parts are there. We pour it in it, we make it out, and do the subtractive manufacturing, do the homogenization. This is the heat treatment process, is the homogenization process. Like Nigel said before, he told that about a muffle furnace. Here it's actually industrial shop floor furnaces, about 20 ton of size. So in that we homogenize it. When we do the non-destructive testings, which is basically ultrasonic testing, radiographic testing, all sort of non-destructive testing, and we do the defect, find the defect, excavate it, repair it, and make the final finished casting. And for that, first we need to make a mold, right? There are two areas where your field comes in. Chemistry, mostly chemical engineers work with us. So those fields are, one is the testing of molds, or how to chemically bind a material to make a mold and of a precise dimension and of the required properties. So there are certain qualities required for a mold. When we are pouring this, and when it solidifies, this, what you're seeing inside, is called as a core. So when a hollow shape is to be constructed, there will be a hollow, it should be hollow, so there should be something inside it to prevent metal entering from there and to make a hollow casting. So that part should collapse. Should collapse once the material is solidified. So it should have a property to withstand the flow of metal and not collapse. And once it solidifies, it should break down into pieces and do not give the casting extra stresses due to its hardness. So it should collapse after some time. So for this, we have several polymers we use to make a mold. So basically, a mold making process it can be classified into several types. We have green sand, which is the conventional age-old process, furan CO2 molding process, and no-bake process. What we use is basically called as alkaline phenolic no-bake process, which is suitable for a medium-sized to large-size castings, we say. So medium size, we can say as 500 kgs to 100 kg, and a large, we can say that 20 to 25 tons, or 25,000 kilograms. So in that scale, when you work, this should work pretty accurately. Otherwise, you'll collapse everything, you'll lose the quality of the product. So just before giving the new technology, I'll just say that this is how it works. This is a sand, okay? The blue particles, which are sands. In between, we need something to bind, right? Like we set cement. So we need a polymer, obviously. So we use a polymer, which is an alkaline phenol, and we use a hardener into it. So it basically sets and makes the mold. Okay? So after half an hour, 1 hour time, in a very convenient temperature of 1600 degrees Celsius, in which we pour the metal. So in 1600 degrees Celsius, we pour the metal, it cools down, it reaches to 1000 degrees Celsius. Then the material solidifies. Then this sand should break down. So that is our requirement. So we have a set of resins and hardeners used for this. And this making process is quite tedious. So we have advanced technologies to make, design, how it should look like before manufacturing. We basically reverse engineer. We'll get the final component. We reverse engineer it. And to allocate all the shrinkages, we provide, like I said, we have the metal reservoirs here, which are called as risers, and paths for metal to flow in. And with all the allowances, this is finally what we should get. And this should be made with sand. So that process is, we make a model. This is how your sand core should look like. And since we are making it by hand, we cannot make all at one stretch. So what different colors indicated are different pieces. So you can see there are 6 different pieces here. We make this through alkaline phenolic process and bind it. So for making 6 pieces, we are making several boxes which are made either of aluminum or of wood. And with all this tedious work, we bind with all the binder, resin, and hardener, we are mixing the sand into it, molding it, and making the cores like this, and we assemble it. Okay? This is the age-old process, what we are using, and it takes so much of time, and like to make the boxes, we are consuming so many materials, and wastage of sand, human effort, pollution. So it's like they are working with chemicals. When people touches it, it's not good for them, actually. So actually, what he is touching is on a coated casting. That coating is basically harmless. We do coat, and then people handle it. So there are several effects of it. So what if we could make this by additive manufacturing? This was thought by some researchers, and exactly I would say there are 2 companies who are the world leaders in this, and we are associated with one of them. They are called Voxeljet. They are from Germany. And now we are equipped with a 3D printing, additive manufacturing facility so that we can make it by rapid prototyping or 3D printing. So it's just an advantage of 3D printing. It's conventional that pattern can be eliminated, so many processes can be eliminated, wastage can be eliminated. And moreover, the most important, I will tell you, you all are familiar with corrosion, right? Corrosion you are familiar with, right? Yes. So apart from chemical composition, when you use a component inside sea or in a desalination plant or in acidic environment, what is the most critical factor about a component that decides its corrosion resistance. It's surface finish. You've heard of crevice corrosion? Yes? So a surface finish should be as good as it can get. And there are some areas where we cannot machine or we cannot do anything to make the surface finish better. So the mold, the sand mold itself should give that much amount of surface finish so that we can use it directly in that environment. So this is the first step of making a rapid prototyping. We should make a model, as I said. We should design the assembly. Then we should go for a 3D printer to make that exact core. So I'll just show you the process. This we are printing a number of cores for a simple casting. So this one was installed by the company itself. It's just a promo video for us. So you can see what that moving is called a head. And it's depositing the sand, the chemicals, and finally we are breaking it out and taking the component. So as you can see, there are so these are components. So in between there is loose sand. Okay? We have resin and hardener. So probably how many of you can imagine that process? What we have done here? It's a very simple thing. Anyone? For a polymer, it requires a resin and a hardener, right? So first, what sand deposited in the entire bed? It will be deposited as layer size of 300 microns or 0.3 mm. It will be deposited all around with sand and resin. Then wherever the required areas of shape in that layer, there only hardener will be given. Okay? So resin is given, hardener is given. Only that required shape gets hardened. The rest of the sand is loose. We can remove it and reuse it. It's a simple process. So by this technology, currently our mold making process, in order to make a pattern, what time required is saved. That wood is, we don't need to cut the wood. So we don't have to make so much effort. So this is our 3D printing facility, which is in Bangalore. So next step, what currently I am working on is, we are planning for a metal 3D printer. We are trying to print the component with printing itself. Instead of subtractive manufacturing, we are moving into additive manufacturing. So this is basically what all the process I have initially told you. Just a 3D file. From that, directly we jumped into casting production. This in between two stages, which almost takes 1 month, is emitted. So due to the surface finish, another 4 weeks can be saved. So it's around 8 weeks. In specific cases, we are saving time. So this is, pattern usage 3D printing technology. You can normally eliminate wood, which is used to make the patterns or molds, and patterns. And pattern lead time, deforestation. So all are green advantages what we use. So I'll just simply tell you an example how important this is. This is a pump casing or a casting which is made by only 4 or 5 foundries in India. It is a 11-stage pump. Okay, petroleum pump, it's 11 stage. So this one has these many cores. If we have to make this by hand, it will take a day. As 2 pieces, we printed the component, finished. Within 4 hours, we started manufacturing. So when we are using this, there are certain challenges. So what you can say is exactly 300 microns. You always see sand. Sand is basically what? Angular, subangular shape, right? It's not of accurate shape and size. So this is usual sand, which you can see more amount, silicon oxide, silicate. Sand is basically silicate. So silicate sand is there. The size and shape is quite different. So it's angular to subangular shape. You need a more accurate material to print that into a precise shape and surface finish. So that is now the new technology which we have taking into account. This is also created by some researchers abroad, which is called as Cerabid. It's a Japanese one, so we are taking it from Japan. So basically, you can see that most of the sand grains are almost spherical. And there are very few number of fines, as we call, small particles in this. And also, I said the temperature in which we pour the metal before, it's 1600 degrees Celsius. Silicate can fuse in that temperature. So a thin layer of sand will be fused onto the metal sometimes. So that also we can avoid with this material. You can see a 23% of alumina there, which is basically Al2O3. Alumina, it will be present inside as alumina. And the melting point of alumina is obviously about 2000 degrees Celsius. It won't fuse. So that problem is eliminated. So with this, we eliminated two problems. We are printing with an alumina-based ceramic bead sand in 3D printing a component which can even used in the most critical applications. So currently, with the conventional process itself, we have supplied even to nuclear. So in Kuthuparamba project, we have supplied our casting. But other than molding, there are certain areas that in the particular customers or the particular industries like NPCL, Nuclear Power Corporation of India Limited, kind of people specifies. That is your material. It should be pure, without inclusion, and that purity, do you think can be given by just by melting and pouring it? There is a process called oxidization. There are several reactions taking in metal. Obviously, you will have a large number of inclusions. So we have to introduce an area of secondary refining. This is also at least a 5-decade-old technology, which through time got refined better, and one of the best form of that we are using currently. So, which is called argon oxygen decarburization, or AOD. So there are vacuum oxygen decarburization, vacuum degassing, and argon oxygen decarburization. So in our terms, we make material like, these are all terms in which we represent materials. This is basically a superaustenitic stainless steel, which has around 20% chromium, 6% moly, and 27% nickel. And all are very highly alloyed. So we are using a lot of metal which has a chance to oxidize and form its oxide inside the metal matrix so that it can cause a number of defects. So in order to avoid that, we can use this secondary refining process. When your team visited our college a few years back, your HOD was also there. So they were most interested in this when we described this process. So your HOD asked me also how this works, like, can you send me a description of that? So this is actually a simple vessel, which is made out of ceramic lining. And we have a plug there to input certain gases. So basically, we classify every gas into either active or inert. So we have one inert gas and two active gases. In that, the most commonly used gas are oxygen and argon, the inert gas. Inert gas, which doesn't react, so we use it for stirring. Make it uniform everywhere and make the reaction uniform happen everywhere in that big vessel. So even though you're seeing it as a small vessel, what we have, the capacity of the vessel is 20 tons. So the vessel is twice the size of me, you can say in height, and breadth will be, it will be half of the stage. So it's a huge vessel. So in that vessel, if everywhere the reaction need to happen with a 10 mm plug, with the gas coming from 10 mm plug, you need stirring. So that argon will be used as a stirring gas, and then oxygen will be passed to react with the materials present inside. So basically, what the reactions happen are, initially, we need to purge all the impurities or whatever is affecting the corrosion resistance outside. So first one, carbon out, silicon out, and we have a much needed element inside there, chromium, but that also has an oxidizing characteristic that also goes out into the slag or the impurity layer formed, oxidized layer and the impurity mixed reactive products formed above the metal, molten metal. So from that layer, we have to get the chromium back into the metal, and that is the next stage. We add calcium, it reacts with the oxygen, and basically the slag will be removed before the oxygen is getting, before more chromium comes into the slag. So first silicon will be removed. This carbon will be gone as carbon dioxide, it goes out, and basically only chromium remains in the slag. So once, to know whether the stage is reached, we'll just take the slag out, cool it in water, and break it off. You can see the color, it's kind of green. So we can say that chromium is there in it, everything else almost gone. That's the meaning of that. After that, what we do, we add lime and stop the supply of oxygen, only argon goes in, stirs, chromium kind of comes back into the molten metal, and due to argon stirring, it gets mixed up uniformly. And with this, most of the impurities, we consider aluminum as an impurity also because it affects some kind of properties. So all such elements which can be oxidized goes out, and materials comparatively clean. We get the chromium back, and we pour it. We get a material property of required minimum strength and impact toughness, even at minus 196 degrees Celsius, and some cases at minus 46 degrees Celsius. So according to the requirement. So this is a mandatory requirement for the nuclear castings and especially for intercontinental gas pipelines. You might have heard of a Trans-Canada project. For that also, this refining process is a main requirement. And in future, like I said, we are going into 3D printing of metals itself. And we are working on some alloys development, which will be pure metallurgy, which will be more than boring to you, but interesting for us. So in last few years, I think 2 years or 2 and 3 years, we have received several recognitions from national agencies and from some of our customers as well for making several innovative castings. So basically all our innovations are related to engineering, less related to chemistry. Sorry for that. And thank you for the opportunity given. Open for questions. Thank you.
Avoid the fact that several emerging innovations are coming right here and you are implementing those. I have one correction though. Metallurgy is
A part of chemistry.
Metallurgy is celebrated chemistry, or metallurgy, my teacher used to say, metallurgy is dirty chemistry.
Yeah.
So having said that, let me, in the context of this corrosion inhibition, I was thinking that the casting that you have, you said alumina is better because silicon oftentimes gets into the molded part, aluminum it reduces, right? Now, it is possible to have low temperature carbon growth. So you can get graphene on the surface of this molded part. So as a result, as you know, carbon is it doesn't melt. You know, the melting temperature is over 4,200 degrees centigrade. So therefore, it is probably possible that advanced coatings of carbon can be made using graphene by low temperature methods. There are low temperature methods which will not affect your casted, what is this, your mold.
Okay.
So this is an interesting possibility, I thought, when you mentioned it.
So thank you, sir, that we should discuss on that in future also. I'll just show you one, yeah. Those people are working on that, right? That is, I told there is some kind of coating on that. That coating actually we made that's zirconia based.
Yes.
It's a zirconia based coating. It is supposed to form a film in between the molten metal and the sand, of course. But the problem what we are facing is, it's a problem we are facing, this coating kind of is stable when a thickness is up to 4 inch and a riser size of around 350 mm is there, and up to that it is stable. When the metal thickness goes above that, we have castings, I told you, even though the component weight is about 15,000 kilograms, the liquid metal used will be around 27 tons, 27,000 kilograms. So in those sections, this coating is not working. Very huge sections, it is getting peeled off or some kind of, it's not stopping the metal from reacting the sand mold. Maybe the heat is excessive for that. So in those contexts, maybe you can help us in that. We'll continue the discussion.
So I just wanted to add one more point that today there is a startup with us
Okay,
where the rockets are being 3D printed.
very nice. So I'd like to talk to them.
Yeah. So it is advanced 3D printing with extremely high quality surface finish.
Okay.
The variety of materials with heat resistance is possible. Just stop there and then we can discuss this further. Okay.
Yes.
Thank you, Dr. Nygil Thomas.